m is much less than n, let us say, and you want to know whether the pattern P exists in T, and sometimes you may want to find all occurrences of the pattern in the text. Okay. And what does occur mean? It should occur contiguously, right? It is a substring. I P is okay. So, a naive algorithm would be, you slide your pattern P on the text, and as long as you are matching character by character, it's good. The moment you find a mismatch, you shift your pattern and keep trying. Or even if you find the match, because if I want to find all occurrences, you shift the pattern by one position and keep trying, right. So, this could take how much time in the worst case? It could be mn, because you might try up to it might match up to m minus 1 positions, and then you and then it has a mismatch and you shift it. Or if you want to find all occurrences, even if you found a match, you may want to shift it. So, this is order mn in the worst case, and you want to improve this running time. Okay. So, how many of you have seen the improved algorithms? You have, some of you. Okay. Fingerprinting, okay, but KMP algorithm? No, okay. Okay, so the goal is to get, in fact, by the end of the lecture, we will actually get an order m plus n algorithm. But towards that, let's look at the following question. Suppose I give you, are allowed to pre-process P. So, let's say so that's my pattern, and I say, okay, you pre-process it in whatever time, because pattern length is m. So, some function of m time you are allowed to pre-process the pattern. Now, I want to check whether my text has this pattern in linear time. Okay. In fact, you should be able to even test for this pattern occurring in multiple texts. So, I can keep giving you text and you should be able to run it in order time proportional to the length of the text. Okay. So, what would you do? What is the natural thing to do? Okay, let me ask a leading question which should give you hints. So, suppose I want to find all strings that contain the pattern AB, ABC, B. What would you do? Shift yourself to some other course you are doing. I want to accept all, okay, now I said, instead of saying check, I want to say accept all strings that contain pattern AB, ABCB. Build a finite automata on the string AB, ABCB, right? And then you run your text. That running the text will just take linear time, right? One pass through the automaton, and you will be able to not only check the occurrence, you will find all occurrences itself, right? So, build a DFA on to accept strings containing P, and then run your text on the automaton. So this is clearly an order n time. In fact, one pass through the text. Once you have the automaton, you run through the text, just read one by one and start from the starting state. It takes you to the next state and keep going. And whenever you hit the final state, you know that you've seen the pattern and keep moving, right? Now let's look at how much time does it take to build your automaton, right? So if I want to construct an automaton that accepts all strings of this type, let's say AB, AB, CB, then so this is a starting state, Q naught. When I see an A, I go to Q1. When I see a B, I go to okay, so this is the final state, right? It's not a complete DFA yet because I have to explain transitions on other characters from each of these states. But suppose I want to accept, look at all strings that, and I want to accept all strings that contain this pattern AB, AB, CB, then here is a starting point for DFA. Now, what do I do if I see a B here? Stay there, right? What do I do if I get an A here? Stay there. Okay, if I see a B here in Q2, go back to Q naught, right? Okay. Of course, I will ask you formally in general what do we do, but let's do it for this pattern. Okay, I see an A here, then where do I go? So if I see a B, I am going to here. So this is, yep. Oh, so this is B, sorry. Yes, correct? Yeah. Because if I see an A, I go here, right? So from Q3, if I see a B, I go here. If I see an A, where do I go? Q naught or Q1? Q1, right? So if I see an A, I mean, I'm looking for AB, AB, but I see an A, so I go to Q1, right? We'll formally figure out exactly what that state we go to, right? And then we will know how to build the DFA, and then that will tell us the time to build this DFA. Okay, from Q4, if I see an A, where do I go? Oh, I also have to tell you, right, where, if I see a C, what to do, right? Because I complicated myself by making the alphabet size 3, but hopefully, I think if you see a C from any of this, you just go back anywhere. So if I see a here, what do I do? No, really? If I see an A here, Q, no, if you go to Q1, you're going to miss this pattern. So it's not, you don't have a choice. It's a deterministic finite automaton. So if I see an A, I have seen an A, B, and A. So if I see an A, B, and A, I should go back here, no? Right? Because A, B, A match has come. So I should go to Q3. Okay? Because if you go to Q naught, then you might get a C and you will realize that the pattern is not there, but actually it's getting there, right? So, okay. So from here, if I get an A, what do? I pretty much go back to Q naught. Q1, okay, if I see an A, correct, good point. Because I've got an A, which is a good thing for my pattern. So I go to Q1. Okay, so if I reached all this way from Q naught, I have found a pattern. Now I am interested in this question where I want to find all occurrences of the pattern. So here I might just output saying, I found there is a success in whatever position in the text I am in minus the pattern length starting from there. Now I want to find the next pattern. So where do I go? I have seen only a B, which doesn't help me anything. So I just go back to Q naught. If I see an A, no, if I see a B, okay, if I see an A, then I can go to Q1. Okay, so now we are into this question of how do I construct in general this DFA given the pattern? Well, the starting point tells you that if the pattern length is M, I can construct M plus 1 states 0, 1, 2, 3, 4, 5, 6. So my DFA has Q0, Qm plus 1, sorry, Qm, and my accepting state is Qm. My alphabet is, of course, the alphabet of the original text in the pattern. The important thing is the transition function now, right? What else do I need for, so I need to give, if I am in some state Q and I see a symbol, some A in sigma, where should I go is the question, right? So at least on this example, you all told me that, oh, if I see from Q3, if you see an A, you go back to here. This is a more interesting example. From Q4, if I see an A, you actually go back to Q3, not all the way back. Why? Why did we, what is the invariant? Okay, so if I am in Qi, what does that mean? Let's understand that, right? What is, if I am in state Qi, what can you conclude? We have matched I characters of, right? We have matched I characters of the pattern. Right? If you are in Q naught, I haven't done anything, and if you have reached Q1, that means I've seen one in my text. As I am sliding my window, I have seen one character I have matched. So now this should tell you, if I am in some Qi and I see a character A, where do I go? Okay, so let me just write down some notation here. Let's say Pi. So if my pattern P is P1, P2 up to Pm, okay, this is, yeah, and Pi is basically P1, P2 up to Pi, up to the ith character. And similarly, yeah, you may or may not need it now for text, but let's say, okay. So that means I matched up to Pi. So clearly it's Qi plus 1 if what? if A is pi plus 1. The I plus first character of the pattern is A, then you just go to qi plus 1. That is a easy case. Otherwise, where do I go? Greatest pi okay. So, I am going to say largest prefix of P1 pi A sorry, largest prefix of P1 to Pi, that is the suffix of P1, P2, Pi A, right. So, I look at, okay, I haven't defined what is a prefix and suffix, hopefully it is clear. Prefix of a string is the first few characters. What happened? Are they able to listen? No. Okay. So, a prefix of a string is the first few characters, right. Starting, so prefix of P1, P2, Pm is you stop at some I character and that is P1 to Pi. You can go all the way up to M. Empty string is also prefix of every string. Similarly, suffix of a string is that you want to end at the ending character, but you can start somewhere in the middle. Okay. So, suffix of P1 to Pm is some Pi to Pm. So, now what am I saying? So, where would you go is you look at P1, P2, Pi A. In this, how much have you matched? So, what is the largest prefix of the pattern which you can match? So, if in this, which is also a suffix here. Okay. Is that clear? Agreed. So, the reason when we were here, we matched. So, we are at Q4, that means we have seen AB, AB. Now, I am seeing A, though the pattern says C, but now I want to know what is the largest prefix of the pattern which is a suffix of AB, ABA. Well, that is ABA. So, that is 1, 2, 3 and that is why we went to 3. And this is well defined because empty string is always there, you can always 0 is always there. Maybe there is nothing which is no non-trivial prefix is a suffix of this, then you just go to 0, right. That was the case, for example, when we went to AB. So, pattern was AB, AB something something, and I have seen AB, which, so I have come here. Now, I see a B, I look at the the largest prefix of the pattern, which is a suffix here. Well, nothing, no prefix is a suffix of this. So, I just go to 0 because empty string is the only largest prefix which is a suffix. Okay. So, you can prove formally why this is the correct way to define the transition function using induction, right. Okay. So, once we have set this, then we know how to build the DFA and we can analyze the running time. So, because this is the only thing that you need to define your transition function, and so Q naught is the starting state. So, let us quickly see how much time do you need to compute this for a particular I and an A, right. So, brute force you run through. So, by the way, I do not even need this, right. So I could just say P itself. So if A happens to be Pi plus 1, the largest prefix of P, that is a suffix, would be I plus 1, P1, P2, P3, Pi plus 1. Because if A is also that, then you will go to I plus 1. So I should say length, because prefix is not a number, length of the largest prefix. Okay. So brute force, it can take something like m square time, because there are so many different prefixes, and you just match with this string and see whether it is a suffix, right. So I'm going to guess that whether, so try whether P1, P2 up to Pi, that these two match. If it doesn't, then try Pi minus 1, Pi minus 2, and see what is the largest prefix that matches with the suffix, right. You may have to shift this really. So each one may take m, and you're doing m different checks. So it's m square, and your number of these things would be like m times sigma. So right, number of these transition functions would be, for each one there will be sigma different edges going out of each state. So m times sigma, and computing each could take m square. So this is like an order m cubed time. Again, naively, but can be improved. We won't bother, because I'm going to give you something better later anyway. Okay, so this is still much better than the mn algorithm we saw, because this is m cubed plus n, and if m is sufficiently small, this is pretty good. And it actually finds all occurrences as well, not just one occurrence, because so even here, after you reach the final state, to figure out where to go, you apply the same thing, because I am here, what is the length of the largest prefix that is a suffix of this, and it takes you to that state. Okay. So the key thing is to figure out that this is exactly what you need. Okay. Now I could ask the other version of the data structure question. Suppose I give you a way to pre-process T, and then a lot of strings keep coming, and you need to check whether in this text this pattern occurs, right. Okay, we'll look at this problem next time. But notice that this is actually the more interesting practical problem, right. When you are doing something in your editor, in your file or something, right, you have this huge text file, and you are searching for something there. You will be searching for multiple different things. So it will be nice to spend time proportional to the pattern length to search whether the pattern is there in the text without going through the entire text, right. Imagine Google. It's exactly this kind of a problem, right. You have a huge number of websites, web pages, and you are given a string. You want to check whether it is there anywhere in your website. So this is a really important practical question, and we will do this. Okay. So we will look at this data structure problem next time. But now I'm going to just talk about this clever algorithm due to Knuth, Morris, and Pratt, which gives you an m plus n time algorithm, where essentially it does something like constructs a finite automata, but not spending m cube time, but order m, even independent of sigma. Okay. And the inspiration is from the automata based algorithm, but it's so this stands for Knuth, Morris, and Pratt. okay, independent of sigma. Okay, so what was the pattern I was thinking of? So let's say I have my text and my pattern is some A, B, C. And let's say somewhere I have matched. So I matched this and there is a mismatch here, right, some mismatch here. And the naive algorithm will just shift everything by one character and it will start matching it. The automata based algorithm will tell you that, okay, you had a mismatch here, but depending on what character you see here, it will tell you where to go and continue, right. Here I'm not going to look at the character at all, except for the fact that I found a mismatch. So I'm going to do a shift, but notice that there is no point in shifting and trying from here, because I know that this is not A, because this is something in my pattern. I know that this is not A, so there is no point in shifting by one character if I had pre-computed this information about how much to shift, right. So, and in fact, if I could have pre-computed and I know that actually I can shift by this many characters, and not only that, I don't even have to do the matching here, because I know that this I don't know, this is I don't know what this character is, but at least I know that I can shift by 2 characters and I don't even have to do. So now I am going to compare this with this character, right. C mismatched, but now I have to try something else. Now I will do this shift and check whether A and this character mismatch, and if they mismatch, if they match, good, I will proceed as I would do in this algorithm. If they mismatch, I will again figure out how much to shift, right, because again I know that there is no point in shifting by one character, because I know this is not A, and I know that this is not A either because of this mismatch. So now I am going to go all the way from here and start matching my pattern from this text. Okay. So essentially what I am going to do is to compute this automaton in order m time, but it's not order m sigma time, and because I'm just not going to look at what this character where there is a mismatch is. All I'm going to learn is there is a mismatch, so I know how much to shift. I want to learn that function and pre-compute it. So let's define what that. So pi of I so that means I am at, so having matched, so you matched I characters, mismatched at the I plus first, so now how much to shift? That length is pi of I. Okay. Let's formally define what it is, right, again in terms of this prefix suffix kind of thing. So what is this? How do I compute this? So somehow we define what it is, and then we will compute it, and then having this information I will tell you how to do the pattern matching in order n time. Okay. And then we will come back to see how to compute this. So what is this? How much to shift? Right? So let's come back here, right. This example I said I matched 4 characters, there was a mismatch here. So now how much to shift? And I said, well, no point in shifting by one character, because I know that this is not A. So shifting by 2 characters is good, because I know that this is A and this is B. I don't even have to check and move on. So what is this? Longest prefix, which is a suffix, right. So it's basically length So there is no new character I am looking at. So I erased my delta definition. This looks very similar to that. Length of the longest prefix, which is a suffix of P1, P2 up to Pi. Not quite, because the whole string is also the prefix, which is a suffix. So, proper, yeah. Length of the longest proper prefix, which is a suffix of this. If I know that, then this is great, because I know that, once I have a mismatch, that is the length by which I will shift. Not only I shift, I also know that these guys have already matched. So now I can just move on and compare with the next character. Okay. So let's do an example. So let's look at, my pattern is some A, B, C. So it's 1, 2, 3, 4, 5. So what is this pi? Pi of 1 is always 0, because there's nothing. The only proper prefix is empty string. What about pi of 2? Length of the longest proper prefix, which is a suffix. Well, the only proper prefix is A, which is not a suffix. So I'm going to say 0, right? Only non-trivial proper prefix. What about here? 1, right? Because this is a prefix, which is a suffix of this string. And here 2, and here it would be 0. Okay, let me do something slightly bigger. So if it's A, 3, right? And here it's 0, and here it's 1. Okay, so suppose I have, it has a very similar flavor to the transition function, but I am not depending on what the next character is. It's just, so it's sort of a prefix function. So now suppose I've computed and stored this. Now let's see how I would do my text matching, right? So first step, compute pi function. We'll come back to how to do this. How do I compute this pi function later? Suppose I've pre-computed it. So now my algorithm looks like this, right? Q is how much I have matched. So for I going from 1 to n, now I'm running my text. So if I did not have a match, is not equal to P of Q plus 1, then what do I do? This is a very similar flavor to the how you run your text on the automaton. So Q is the number of characters you have matched, which is 0 initially. So now I check the first character of the pattern and the first character of the text. If they match, good, I am increasing Q, and if I have reached the end of the pattern, then I output success and move on. Let us see how I would use Q. So, if I do not have a match, Ti and Pq plus 1 do not match, I need to know how much to shift my pattern from. My pi function tells you. So, I shift from Q to pi Q, and then now I check whether Ti and this next P, because I know up to pi Q I have matched already, right. That is exactly the property of the pi definition. So, now I check whether the Q plus 1 character and whether Ti matching. If they match, I move here. If they do not match, I shift again. I keep shifting, and eventually I might become Q might become 0. I have not matched anything at all. Then I come here and check whether first character and Ti are matching. If they do, fine. Otherwise, I move my text. So it's the way I have described this algorithm, right, in the picture. A B A B A C A. So let's say I have some. So I run my pattern. I would have A B matched. So Q would have gone up to 2, but then in the next character I am not. So I would have also moved. Here I am not matching. So I would shift to T2 pi 2, which is 0. So I will go all the way from here and then start testing for this. Okay, I will compare this B matches. So if I do not shift all the way back to 0, then I know how much I have matched. I will match the next character and move on. Okay, so hopefully this code is clear. But it's what is not obvious is that why it takes order n time, right? Because you are checking, with one particular character, I may be doing a lot of comparisons here as I do shifts, right? But other than that, hopefully the correctness is not hard to see, because it has this very similar flavor as how we would do it in the finite automaton. Okay, so if you do succeed, then again you shift, you know how much to shift, and start checking from the next character of the pattern. Okay, so the complicated part to analyze is that this while loop. So this happens only, there is one step in each of the loops. The for loop goes through n steps. This is a constant time operation, but in the while loop I am spending a lot of time. So why does it overall run to order n time? Okay, we will do some sort of an amortized analysis. Okay, come up with some nice potential, and then so basically what's happening is that I have, let's say, matched up to some huge long length of the pattern, and there is a mismatch here. So far so good. When there is a mismatch, I do some shift, and then I compare this character with this. Mismatch again, do some shift, this character with this, and so on, right? So it looks like this character is compared several times. So, but there must be some other progress happening, which is that this pattern is moving to the right every time that happens, right? So can you think of some potential to argue that this while loop, okay, there are a couple of ways to analyze this. So, is the algorithm clear, and is the problem of the analysis clear? Right? So subtle why it takes linear time, but there is a very simple proof. Yeah, so the key thing, I mean, when I want to do amortized analysis, what if at some step, if the algorithm takes long time, there's something else which should capture the progress, right? When you're doing some multi-pop or something, then the stack became something very small. So here what's happening is that if you are comparing with this character several times, Q is becoming smaller and smaller. Q, the number of characters you have matched, is becoming smaller and smaller, right? So let's define Q as our potential. Okay. Since and you know it's a proper prefix and so on, so this length is strictly less than I, right? Pi of I is always less than I. Okay, so in particular, Q keeps decreasing at every step. Q starts with 0. What is the maximum value Q can get? Yeah, Q can get maximum M, because the moment it reached M, it comes back, it is decreased again, right? But I don't want to talk about maximum. Okay, number of times Q is increased. Can you say this? Q's value may be maximum M, but how many times Q is increased in this entire program? Maximum. Where is the increase in Q happening? In this step. This is the only step, right? And that is exactly once every step of the loop, right? So it's at most N. Right? Q starts with 0. You know, I mean, think of this number Q is just pushed around. It starts with 0, then it increases, and then it decreases, increases, decreases, increases. It goes like this. But the number of increases is at most N. Okay. So the number of decreases cannot be more than N, because Q is never negative. Okay. This is like this push pop stack analysis, right? The number of pops cannot be more than the number of pushes. It's that kind of an analysis. So yes, this step is executed several times in the for loop, but you know, you can't just, yeah. So that's it basically, right? So if you think of, so that's one aggregate way of analysis, that number of times Q is increases at most N. So number of times Q is decreased is also at most N, because Q is always greater than or equal to 0, right? We never, in the program, we never make Q less than 0. And Q decrease is happening here. So this is overall in an aggregate way, so that's order N. Okay. Another way to think about it is just write down potential of my structure as Q. Then if this step is taking a long time, then Q is dropping by that much, right? So the amortized cost is offset by a big drop in the potential. So the actual cost is some L, means the potential will drop by at least L. And so here the actual cost is 1 and the potential is increased by 1. So there is an amortized cost of 2 here. This is a constant time. So okay, so overall, okay, this is a very subtle analysis, has a amortized complexity flavor, but it essentially mimics what we were doing in the automata thing. Okay, so now I haven't told you how to compute this. If I have pre-computed this pi function, then we can run and do my pattern matching in order n time. Now, how do I compute pi? It has a exactly similar flavor, because what we are doing here is testing my pattern with the text, whereas to compute pi function I am testing the pattern with the pattern itself. Okay. So, it has exactly similar flavor. I will write down the code, but I am not going to do the analysis. Okay. So, here therefore you can so if you use okay. So, computing pi. So, I know that pi of 1 is 0. So, I do not even have to do anything. Okay. So, suppose I know up to pi of q, right. So, I am trying to compute pi of pi, and I know that 1, 2 up to some q I have computed this. And I want to compute for pi of q plus 1. Remember what the definition of this is, that if you are looking for the longest proper prefix, which is also a suffix. So, if this was some k, that means that 1 to k is a proper, it's a prefix which is a suffix here. So, if k plus 1 and q plus 1 match, yeah, okay, I am looking for q. So, I have seen up to q minus 1 and I am looking for q. So, if the k plus first position and qth position, if they match, then I know that this guy is basically k plus 1. If not, if they do not match, then I know how much to shift by based on the pi function, but this pi is for the smaller k, which I have computed before. So, keep shifting and essentially running something like this code, and you find the proper k and assign pi of q to k. Okay. So, again if 1 to k is a proper, is a prefix, longest prefix, which is a suffix of 1 to q minus 1, and if k plus 1 and q match, then the longest prefix, which is a suffix of 1 to q, would be k plus 1. If not, if these guys do not match, then I have to do some shift here and compare that with this, and I keep doing this shifts like the way I did for my text matching, and find that particular k, and that is what I am going to assign for pi of q. It could be 0 as well. Yeah. So, the correctness and the running time exactly as we analyzed for this, but here it is order m. Yeah, so here also the while loop is executed multiple times, but if you use a potential like k, then you can see that the amortized cost is constant. Okay, so that's a nice clever algorithm due to Knuth, Morris and Pratt in 1970 something. Okay, so let me spend some time on the other pre-processing problem. I said that if you are given the text to pre-process and now I want to check whether some pattern exists in the text, how fast can we do, right? Okay, this is so you have this huge text. So text size is very large, and pattern size is m, which is much less than n. Now the goal is pre-process text, in reasonable amount of time. I mean, ideally, if I want to compete with KMP m plus n time, I want to do it in order n time. But if you think of it as this larger practical problem of I have this huge text which is pre-processed once, right? Concatenation of all the web pages, for example, and then these queries are coming hundreds of thousands every day, and you want to answer queries fast. How fast? So pre-processing time is important, but I'm not going to pay too much attention to it now. But so that checking occurrence of P in T, checking occurrence or all occurrences. How much time we want to spend? Order m, right? Right? Imagine, I mean, I don't want to have anything to do with n here, right? If I have a query to give it to Google, I don't want it to spend time proportional to length of the text. I would rather have it proportional to length of my query, which is the pattern length, right? The fact that you can do it is what makes it, interesting and useful. In fact, I can find all occurrences. Google does it, right? It gives you all, it gives a ranking of everything. And there are lots of variations of it. You can have some weights for these pages, and you want to find the top k occurrences, all kinds of things. Okay. So the data structure which is really enabling us to do this is what is called suffix trees, which is a lot of use. So what is a suffix tree, right? So let's say my text is some T1, T2 to T n characters. Okay, let me just explain what a try is, right? So I have a set of strings. And what is a try? Well, it's a tree. Each edge is labeled, it's a rooted tree. Each edge is labeled with a character. So I will have something like this. Okay, so the leaf, maybe I'll store this as A, B, A, C. And then I have B, A, A, B, C. I'm going to share this edge A. And A, C, B, D would be so that's a try for a set of strings. What is a try? It's a rooted tree, edges having a label as a character. And then if you read a root to leaf path, that corresponds to one string, right? So rooted tree, edges labeled with a character from your alphabet, and every root to leaf path corresponds to a string in my set. So it's actually try, yeah. All right. So have I captured everything in the definition? Yes. Right. Okay, and so each child, every edge has out of a node has a unique character. Okay, so no edge which means that I can't have two children with A, for example. Right? If you need it, share that edge A. Okay, so is the definition of try clear? So a suffix tree is a try, so suffix tree of a text T for all suffixes of T. So what is this useful for, let's say? So if I want to know some string is in this set, I give you a string, A, B, A, B, A, B, and I want to know whether it is in the string. How much time does it take to figure that out? Length of the pattern, really, right? You run through the text, not necessarily height of the tree, because I may have a very long string here, but it's actually proportional to the length of the pattern you are querying, length of the string you are querying. So if I want to know A, B, A, B, A, B is there, I start from the root, I traverse to A, and then I find a B, and then I find a A, and then I find that there is no B out of this node, so I can stop and say that my string is not there, and the time I would have spent is proportional to the length of this query string. Okay. Okay, so I can just say can check for membership of a string x in S in time order length of x. Okay, so now what is the suffix tree of a text? It's a trie for all suffixes of t, right? So what are all the suffixes of t? Well, t1, t2, tn itself is a suffix. T2 is a suffix. Let's call the suffix starting at position 2. T1, T2, Tn is a suffix starting at position 1. So there will be Tn, which is a suffix starting at position n. So build a trie for this set of strings, and that is a suffix tree for this given text t. Okay, good question. So what is the problem?
Because I don't know whether, like, if I'm AA, I'll go to AA, but I don't know if that element is in the second.
Good question. So his point is, let's say I will search for AA in this here. Then I follow through A and I get an A, and then there is nothing coming out of it, but does it mean that A is in there or it's not in there? Okay, good. So let's make that assumption that no string is a substring of other. Okay, then I mean, one way to fix the problem, yes. So I add some dollar here. Okay, but that's same as saying I can ensure this by adding a dollar. Yeah, basically I'm adding a dollar everywhere. The character which is not there in my alphabet, and I add it everywhere, and then I look at that string. So that means I'm just going through the dollar. Okay, so in particular, if I want to ensure that for here, then I just add a dollar here, right? So it's a tn plus 1, which is dollar. So all of this, so no string is a substring of the other, because one of the things I said, every root to leaf path corresponds to a string in S, and I want this to be conversely that every string is in some root to leaf path, right? So in particular, if A is in the text, it is not in the root to leaf path if you have this problem of one string a substring of the other. But one way to fix that is to add this dollar. Okay, good. So now what is the suffix tree? Well, you are given a text t. I write down all its suffixes and build a trie on that. Okay, and that is a suffix tree. Okay, so suppose I add a dollar here, then so I will have a node which is a dollar, a node which is a dollar. So this is okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a string suffix starting at position 9, suffix starting at position 8. BA dollar would be looking like this. 7, ABA dollar would be like this. Suffix starting at position 6. AABA dollar would be like this. BAA dollar would look like BAA. and you get the idea, right. So, the pre-processing time is actually the time to build this suffix tree. There is one other thing to worry about is the space for this suffix tree, which is huge, right. These are some of the issues. The pre-processing time, space. Naively, what is the pre-processing time? If I just take each suffix and run it and insert it in the text. If I have a text as length n, I take one suffix, create a path, and then I take another suffix, run it on this path, because I can't have two children with the same character. So, wherever I run out of it, I start my new path and continue, right. If I naively do that, that would take how much time? N square, right, because there are string of length I plus 1, I plus 2 from all the way. So, this is going to be n square. How much space it is going to take? How many nodes are there in the worst case again? Order n. Why? There are n or n plus 1 leaves are there, but I could have up to n square. So, in particular, let us say all characters are different. Okay. Then you are just sort of creating new path all the time, right. So, these are sort of issues to worry about. We will deal with them, try and improve them. But the important thing, what is the important thing? The query time. Okay. I want to know whether P exists, right. That is what if I want to find. So, P exists or occurs, that is the word I am using, T if and only if, is a very extremely hard lemma, P is the prefix of some suffix of T. Right, really trivial, right. P occurs in the text if and only if P is a prefix of some suffix of the text, right. If P occurs in the position I to I plus m, then P is a prefix of the suffix starting at position I, right. So, how do I check whether P occurs in the text T? Well, just run it on this tree, and if it's a every suffix is represented here. So, if P occurs somewhere, then it will just come and you will find it as a prefix of some suffix, and in time proportional to the length of the pattern, you will know whether P occurs or not. Right, and how much time this takes? Order length of P. Right, this is our goal anyway. If I want to find all occurrences of P, how can I extract that from this? So, let us just to go through. So, if I want to know ABA occurs, then I just follow through A, B and A, and I know that yes, ABA occurs. But I want to find all occurrences. Can I extract it from this suffix tree? So, for
number of leaves you will have from
yeah. So, first of all, ABA occurs, where does it occur, right? If I want to know where does it occur in the text, well, you follow through the entire path and go here up to the leaf, and it tells you position number 6 is one place where ABA occurs. But it might have another thing, well, because ABA appears here, you will also have a suffix which is ABA and then AABA dollar, which will have 3 here. So, if you follow through, so in this entire subtree, all the leaves correspond to the occurrence of my text. Okay. So, for example, I could, if I really care only about the number of occurrences, in my pre-processing, I could store at every node the number of leaves in the subtree. And if I store that number, then when I get there, I know that how many occurrences are there. Okay. But if I really want to find the position where it's occurring, well, again, I could pre-process and store them in my node. I mean, I'm already said n square space is too much, but I'm adding things. But if you care only about the query, for every node, I can store the position at the leaves, and then I can store that set in my subtree. What are all the leaves, and store that in my node. Then when I get there, I know all the occurrences. I know number of occurrences. I can output all the occurrences and stuff. Okay, and all in time proportional to this, because I just get there and then I'll get it. Okay, so but there is a way to construct this suffix tree in order n time actually. So if you apply that, then it's sort of competing with KMP algorithm, because you can, given the text, construct it and then run your pattern m plus n. But this is really useful only when you're doing this pre-processing once and you have lots of queries, which is where a lot of natural applications are. Okay, so next time we will one way to reduce space. Let's think about it. What is causing n square space? Okay, think about it. It's just a tree with n leaves. Why do we have too many nodes? Yes, because of nodes with exactly one child, because they are contributing to too many nodes here, right? So one optimization you can do is to concatenate all those guys, and instead of having, so basically make sure that every node has at least 2 children. So if you have only one, make that into a single edge, put the label of that edge. Now your edges will not have just a character, but it will have some substrings. Okay, does that make it order n nodes? That alone, is that enough? So reducing space. So I don't know what word to use. So if a node has only one child, then I'm going to say transfer its label right. So if I have a node which is exactly one child with some character a, then I'm just going to say this may have some x, so I'm going to write this as xa and delete this. Right, of course. So not really delete, but I don't know, concatenate, but you know what I mean. So what have we achieved at the end? No node has exactly one child, right? And the number of leaves is n plus 1. one for every suffix. So, so really every node is, if you think of it as a tree, every node has degree at least 3 except the root and the leaves, right. So, how many high degree nodes can a tree have? But by high I mean greater than or equal to degree 3. Yeah, because just, what is the average degree of a tree? Average degree is at most 2, right? Why? Because the total number of edges is n minus 1. So, total degree is at most 2n minus 2. So, the average degree is at most 2, right. So, you cannot have too many vertices with degree more than 3 unless they are compensated by somebody with degree 1, but there are only n leaves or n plus 1 leaves. So, you cannot have the remaining vertices cannot be more than n. Okay. So, I will leave that as an exercise, very simple. A tree with n leaves and no degree 2 n minus 1 order n something, right. This is, it's really an interview question. Okay. So, it's something I told you everything about why it is the case. So, you should just use the degree argument and you will see that the high degree vertices cannot be large. So, yes, so if you just do this optimization, since there are only n plus 1 leaves, you can make sure that the number of nodes is reduced to order n, but they are not the only ones that count for space, because the edges also have labels that you have not reduced, because now the edge labels still remain the same. Okay. So, they could contribute to space. So, we need to deal with them. Okay. So, next time we will look at reducing space and other applications of suffix tree, and maybe constructing, because construction algorithm is not that easy. But the interesting thing is there are many nice applications of suffix trees where you can do some complicated string questions which you would not think of an easy algorithm without suffix trees. I mean, there is no way you can devise such an algorithm without getting to suffix trees. Okay, I think I will